Laplace transforms allow us to solve DEs that have discontinuous forcing functions pretty much just as easily as those with regular continuous forcing functions. Now, to see how this works out, we need a couple of technical tools, and these are what are called the shifting theorems or translation theorems. What they do is they talk about how shifts in one space translate into the image space. So what I mean is, if I were to take the Laplace transform of a shifted function or the inverse Laplace transform of a shifted function, what do they do? What does the shifting do? Does it have a similar effect in the image, or does it do something totally different? So we'll talk first about this situation, the shifting in S or frequency space. So we're going to take the Laplace transform of a function, and remember how it's defined. It's defined to be f of s, and it's defined as this integral e to the minus st f of t dt. Now what's important here is that these s's link up. And really they're a dummy variable, right? So this could be f of blank is 0 to infinity e to the minus blank t f of t dt. So if I feel like it, I can put in whatever I want. So if I put in an s minus a, then what's going to happen here is that I'll have e to the negative s minus a t f of t dt. Now, this is going to require that s minus a be positive for convergence. In order for this integral to actually exist, I'm going to need to do that. But given that fact, what I'm allowed then to do is to split this up. I'll have e to the minus st f of t dt, e to the at dt. And effectively what I found is that, hey, this is the Laplace transform of a different function. This ends up being the Laplace transform of this exponential factor times my original function. And this is what we call the first shifting theorem. And it says the following things. If you ever need to take the Laplace transform of an exponential function weighting something in t space, this ends up being a shift in s space. Or the way that we had thought about it, just by using our regular old switcheroo, is that a shift in s space will translate to an exponential function multiplying in the t space. Now, in my opinion, it's very convenient for you to think of this result in a different way. You should think of this as the Laplace transform of the function f of s, and once you've identified the shift, you can then just think of it as, hey, it's been shifted s into s minus a, and that's going to end up giving me the inverse Laplace transform of this function with an exponential e to the at multiplying it. So that's the first shifting theorem here. Now, here's a very simple example. In my opinion, it's a lot easier to start with the space we motivated this in. So here's the question. Let's say what we want to do is find the inverse Laplace transform of s minus 1 to the power of 4. Now this looks very, very similar to the inverse Laplace transform of 1 over s to the 4, but I'm going to denote this by saying, look, s has been shifted to s minus 1. And that's how I'm going to identify what to do next. So remember that this needs a 3 factorial up top and a 1 over 3 factorial down below. And I'll have this s into s minus 1. This is going to give me 1 over 3 factorial, inverse Laplace transform of 3 factorial s to the 4. And remember, this, according to the shifting theorem, that shift is going to end up giving me a exponential function with a 1 upstairs. So this will be 1 times t. And the inverse Laplace transform here, I'm going to get 1 over 3 factorial. This is going to be t cubed e to the t. So my answer here at the end of the day is t cubed e to the t over 3 factorial. This is how the shifts kick in. We identify the shift. We account for it by saying, look, a shift in one space is going to be multiplication by exponential in the other space. So I identify the shift. I translate it back to its original base function. I determine the Laplace transform of that base function, and then I just weight it or multiply it by this exponential. That's what the shifting theorem is telling me is going on. As a slightly more involved function here, we want to get adept at dealing with shifts and using the right shift. Now, here's another example. I've got this 5s. Now remember, the shift here that I want to deal with, and I can see it very clearly, is an s minus 2. All right, this is the term that I want to deal with, shifting s into s minus 2. Now, the problem upstairs is that I don't have an s minus 2, but I could take this and write it as s minus 2 plus 2. And that's going to be very convenient for me. That's going to allow me to apply the shifting theorem as a whole block for one of the terms, and it'll make it convenient for me to work with. So I'll write it like this, s minus 2 all squared, and because these inverse transforms are all linear, it will make things very convenient. So that'll get split up in that way. This will be a 10 over an s minus 2 squared. I can clean this up. I'll have 5 inverse Laplace transform of 1 over s minus 2 plus 10 inverse Laplace transform of 1 over s minus 2 squared. Now, that doesn't require any shifts. That's pretty straightforward. This is going to be e to the 2t. Going to pop right out. But if I wanted to, I could think of it in terms of a shift. So I could think of this, and I'm going to do that for illustrative purposes. I'm going to say, okay, look, this is the same as 1 over s, where s has been shifted to s minus 2. This is the same as the inverse Laplace transform of 1 over s squared, where s has been shifted to s minus 2. The purpose of that shift is it's going to give me an exponential function. So the shift allows me to see very clearly what the basic function is here. That's going to be a 1. And the shift provides me, according to the shifting theorem, e to the 2t, which is equivalent to what I had found a moment ago. Same thing happens in the next term. I'll get a 10. I know that this is going to give me a t, whereas the shifting function there is going to give me another e to the 2t. So at the end of the day, this is 5 e to the 2t plus 10t e to the 2t. Now, of course, you can go forward. So if you've been given an expression that has exponential functions in it that are weighting or multiplying other terms, the shifting theorem can be used forward. Remember that Laplace transform is linear, just like the inverse, and I should take advantage of that. So I'll have the Laplace transform of 9 e to the minus 3t minus 4 Laplace transform t e to the minus 3t plus 10 into the Laplace transform of e to the minus 3t sine of t over 2. Now, all of these terms are terms that naturally arise from using solving constant coefficient differential equations, and that's all normal stuff. According to the Laplace transform, anytime I have going forward a function, now here's what I need to do, to clean this up to really make it evident. That 9 should go up front, and I should have a 1 down there. Going forward, the Laplace transform of an exponential function that's weighting some other function, the exponential part is just going to be treated as a shift in the result. So really what I want is to say, okay, what's the Laplace transform of 1? The Laplace transform of 1 is just 1 over s, And the shifting part now comes in. The exponential will tell me, hey, this is going to get shifted to s plus 3 minus negative 3. If I subtract a 4, the exponential part is going to be a shifting. The Laplace transform of t is going to be 1 over s squared. This s is going to be shifted to s plus 3 plus 10. I need the Laplace transform of sine t over 2. Well, that's going to be a 1/2 s squared plus 1/2 squared. And then the exponential is going to shift me to s plus 3. So at the end of the day, 9 over s plus 3 minus 4 over s plus 3 squared plus 5 into s plus 3 squared plus 1/4. And you can start to see that the types of expressions we're getting here are more complicated. And that's important because when we start undoing things later, we will be getting these complicated ones.